Hello, everyone. My name is Kaswini Ojuku. I'm a software engineer and a blockchain developer. So, in this video, I'll be taking out time to break down the Uniswap V2 Pair smart contract. So, this is the part two of the first video I made earlier yesterday. So, the first video I explained the Uniswap V2 ERC20 contract and also the Uniswap V2 factory contract. And I was able to explain that, okay, the Uniswap V2 factory contract is a contract that clones the Uniswap V2 pair contract each time a user is providing liquidity for the first time. And I also explained that the Uniswap V2 ERC20 contract is it's a standard ERC20 contract. That's an ERC20 token that gets minted to liquidity providers each time a user provides liquidity on the Uniswap V2 pair contract. That token that is minted to the liquidity provider serves as a certificate or serves as a right that this person it's partaking in a particular liquidity pool. So each time users swap on that pair or swap those two tokens, this person will uh, will partake in the 0.3% that Uniswap charges as fee for trading and all of that. So I was able to explain that in the part one of the video. So in this video, we are going into the main smart contract of Uniswap that handles the swap, handles the liquidity provision, handles the removal of liquidity, and it also contains the function that calculates. It also contains the Uniswap price oracle, which calculates the ratio of each token. For instance, let's say we are working with Shiba and Dogecoin. So the price oracle will tell you the amount of Shiba Inu token you will get when you bring a particular amount of Dogecoin, and it to also tell you the amount of Dogecoin you will get when you bring a particular amount of Shiba Inu. And this contract also handles the Uniswap optional fee. Like okay, like I said in the previous video, Uniswap can choose to turn on or turn off their fee, whereby they'll be getting 1/6 of the total fee that the platform accumulates over time, that the each particular pair accumulates over time. All right, so if you like the content you're getting, don't hesitate to subscribe to my channel and also turn on the notification bell so that you get notified each time I drop content like this. So I'll be doing more of this review. I'll be reviewing more complex protocols like MasterChef, SmartChef for PancakeSwap. I'll be reviewing Compound Protocol, and I'll be reviewing Synthesis and all of that. So stay connected so you get notified each time I review a contract and I break down the codes. All right. So without any further ado, let's dive in. So right now, currently, I'm on the Uniswap V2 Pair smart contract. So this is the left-hand side of my screen is the smart contract itself, while the right-hand side of my screen is where I did my documentation when I was studying the smart contract. So before we move ahead, let's just read a little bit of this documentation. So what we have here, so Uniswap V2 Pair. So the Uniswap V2 Pair.so contract handles the heavy lifting of the entire Uniswap V2 platform. All right, so it handles the heavy lifting. I think is the most complex smart contract in the entire Uniswap V2 protocol. So it contains the main function which handles liquidity provision. It has the burn function which handles liquidity removal. It has the swap function which controls swapping from one token to another. All right, so the V2 pair contract functionalities are managing funds, handling functions for liquidity providers, handling functions for traders, that's the swapping, managing pool ownership tokens, which is the liquidity provider tokens that get minted to users each time they provide liquidity. And it also handle protocol fee. Yeah, that's the 1/6. The 1/6 and the 0.3%. I tell you that each time user swap, it takes that fee. All right. So let's go down now. Here we have code breakdown, Uniswap V2Pair contract. So first, we are looking at the managing funds. So Uniswap pair is an exchange between a pair of token, for example, Dogecoin and Shiba Inu. So we'll be using these two guys as our example. These tokens are represented by token 0, that's contract address of the token 0, and token 1, contract address of token 1 in the pair contract. So, like I said in the previous video, for every for every token you swap on Uniswap, let's say you want to convert your Dogecoin to USDT on Uniswap, there is a pair contract created for that. Let's say you want to convert your Dogecoin to ETH, there's a pair contract created for that. And the pair contract will contain the contract address of the first token and the second token. For USDT and Dogecoin to be USDT contract address and Dogecoin contract address. For Ether and Dogecoin, now Ether doesn't have an address, so Uniswap now makes use of what they call WETH. So that WETH is called wrapped ETH. That's what they use to represent Ether. So that Ether is that WETH is what they use. So whenever you're swapping to Ether, or if you're swapping to Ether, that WETH will if you're swapping to Ether, what they use basically is WETH to keep track of the token in the pair. You understand? So they use WETH to keep track of the token in the pair. But at the end of the day, the WETH is bond and Ether is given to you. So that's what Uniswap is doing and all of that. So as I was saying, the tokens are represented on line 88. The tokens are represented by token 0, that's contract address of token 0, and token 1, contract address of token 1 in the pair contract. So let's look at this. Before we continue with this reading, let's move over here. So let's look at the contract. So on line 1, we have our version declaration, which is 0.5.16. And on line 3, this is where we are importing the Uniswap V2 pair. So like I said, the Uniswap, this is an interface. So I always repeat this so you don't get confused. There are two ways to use interface in Solidity. You can use interface for implementation. You can use interface for interaction. When the interface is imported but is not inherited by the contract where it's being used, that means you're using that interface for interaction. But when the interface is inherited, that means you're using that interface for implementation. You understand? That means you want to implement the functions in that interface, and you must implement all the functions that the interface contains, else Solidity will throw you error. All right. So here we are importing the Uniswap V2 ERC20 token. So this is the ERC20 token that gets minted to liquidity providers when they provide liquidity. We are importing it as well. The reason why we are importing it and we are inheriting it is so that we have access to the functions of this contract. So once you import, you have access to the functions, especially the mint and the bond functions. That's what we'll be using mostly here. All right. So we have the libraries math.so. So this math.so is it's a library used when you're performing mathematical operations in Solidity. So it helps save against overflow and underflow. I won't be explaining overflow and underflow. As a smart contract developer or a blockchain developer, you should know what overflow and underflow means. All right. So on line 6, we have this library UQ112 times 112.so. So now we all know that Solidity doesn't support floating numbers. Like it doesn't support floating numbers and all of that. Where you have decimal, Solidity doesn't support decimal. So this library is used to handle those floating numbers. It's used to handle fractions. Yeah. So just take it like that. Just know that this library is used to handle fractions, floating numbers, decimal, and all of that. So you can check this library out to see how it works. I don't know. I might be, I might be happy enough to explain it. But let's continue. If maybe if I can't explain it, I will. But for now, let's continue. All right. So on line 7, we have the IERC20. So this is the IERC20 interface. Yeah. So like I said, this guy is also imported. Like, and I think this guy will be used for interaction, not implementation, because we are not inheriting it here. Then on line 8, we have the iUniswap V2 factory. So this is the interface for the Uniswap V2 factory, which we explained in the previous video, in the part 1 of this video. So if you don't understand what the factory does or what the ERC20, the Uniswap ERC20 does, you can go back to the part 1 of this video, watch it before coming back to the part 2. Then we have the Uniswap V2 Collie. So this Uniswap V2 Collie is just like when you're swapping, if the person that initiated the swap transaction initiates the transaction, this V2 Collie um, notifies the user or the trader that okay, you're performing a swap event and all of that. So we'll see where this guy is being used while we continue in the contract. So just take it like, just understand that this guy is used to notify the trader that is performing a swap transaction. All right, so enough with the import and all of that. Let's now move to the contract proper. All right, so on line 11, we have Uniswap V2Pair is iUniswap V2Pair. So it's inheriting the iUniswap V2Pair, and it's also inheriting the ERC20 contract. That's the Uniswap ERC20 contract. So here we have using SafeMath for uint. All right, so this is so there are two ways to use libraries. You can use the library like by just calling the name of the library dot the function you want to use in the library and make use of it, or you can use it like this, using SafeMath for uint and using UQ112 times 1124 uint244. So this is another way of using a library. So once you do this, you can always use this library wherever you want to use it. Okay, so let's proceed. So if you want to understand the various ways of using libraries and all of that, you can study more about libraries. All right. So now here we have the minimum liquidity. So this minimum liquidity, it's set here so that this is set and used to avoid division by 0. All right. So when liquidity is being calculated, like when a liquidity provider provides a liquidity and Uniswap wants to calculate the amount of token that will be minted to the person, there's a calculation that is being done that requires that they divide by something. So we'll see it when we get to that that divides by a particular denominator, and it makes use of liquidity to do those division. And if we don't set maximum liquidity, it will get to a point where liquidity will be 0. So if, for instance, now, when you provide liquidity, you can also remove your liquidity. So if users remove all their liquidity, at some point, liquidity will become 0. So, but with this minimum liquidity, liquidity can never get to 0. So the minimum liquidity is this 10 raised power of 3, which is obviously 1000. This is the minimum liquidity. So it's used to avoid division by 0. Then here we have byte for private constant selector. So Uniswap is making use of low level core when they are performing their transfer operation. So if they want to transfer, let's say you want to transfer in your swap, or if you're providing liquidity, a token needs to be transferred from one person to the other. So, but Uniswap ensure that they did a lot of gas optimization. So because of that, they are making use of low level calls in their transfer. And one of the way to make use of low level call is to use the call function, the Uniswap call function. And with the Uniswap call function, you can do something like ABI encode with function, ABI encode with selector, and you pass the function selector of the particular function you want to call, then comma, you put in the values and all of that, and it will call that function for you using the function selector and the values you pass. And that is a more gas optimized way to perform that operation, and that's why Uniswap is doing that. So now what they are saving here is the function selector of the transfer function. And if you're advanced in Solidity, you understand function selector. You know that, yeah, function selector is basically the name of the function and the function type, like the type of the parameters or the argument of the function. So that means this function will be taking an address and a uint. And mind you, whenever you're making use of function selectors, if you're doing stuff like this, you have to type in the type completely. You don't. We know that if you type uint, it's the same thing as uint 256. But when you're doing this, you have to type it completely uint 256. Don't just put uint there. All right. Okay. So with that said, let's move over to line 18. So line 18 is a state variable called factory. So like I explained in the previous video, when you're deploying this contract, it is a factory contract that deploys this V2Pair contract, right? So now this factory variable here holds the address of the factory contract that deploys this contract. That's why if you check your constructor, where's our constructor? Let's look at it. If you check your constructor, yeah. So once you deploy this contract, the factory is set to the MS user sender. And since the factory contract is the guy deploying this contract, automatically the MS user sender is the address of the factory contract. All right. So that said, yeah. So what is being saved here is the address of the factory contract that deploys this pair contract. Then the token 0 and the token 1. So these are the two tokens that this pair will be swapping. So when this pair contract is created, there's a function called immediately after the contract is created. That function is the initialize function. This is it. So this initialize function takes in the address of the two tokens that this pair will be swapping, like this pair will be handling. So this is the address of the first token and the address of the second token. So the address of the first token is called token 0 and the second one is token 1. So once this is passed, it will now set whatever you pass here to the token 0 state variable and whatever you pass here to the token 1 state variable. So Discord is giving me notifications. Let me close it once and for all so we don't get distracted. Quit this guy. All right. Okay. So this is it. So this guy sets this initialize function sets this token 0 to this guy and this guy to this guy. And yeah, and this is called immediately this contract is deployed. So that's why we have this variable here. So this is just the address of the two tokens that this pair contract will be handling. All right, so let's move over to the line 22 where we have the reserve 0. So reserve 0 keeps track of the amount of token 0 that this contract has. You get? So it keeps track of the, when you're providing liquidity, you're bringing a particular amount of token 0 and a particular amount of token 1. So that amount of token 0 you're bringing when you provide liquidity is what this reserve is holding. And the token 0 is for reserve 0 and the token 1 is for reserve 1. Get that? So let's look at my documentation at the right hand side of my screen so we can get this guy. So okay, yeah. Okay. We have talked about tokens are represented by token zero, contract address of token zero, and token one, contract address of token one in the pair contract. So reserve variables store how much of the token the pair contract has. So reserve zero is holding amount of token zero in the pair contract, and reserve one is holding the amount of token one in the pair contract, right? So and token zero is the contract address of token zero. That's one of the token of the pair, and token one is the contract address of the second token, right? So that said, let's look at uh, block timestamp. So block timestamp keeps track of the last time the reserve was updated. So now this is what happens here. When you provide liquidity for the first time, block timestamp is holds the time that liquidity was provided. Now, when someone provides liquidity again, that means this reserve is updated because new token came into this contract. Block timestamp also gets updated to that time that was done. When liquidity is removed as well, that means reserve will change and this will change. Block timestamp too will be updated to that time. When swap operation happens, when there's a swap, and remember when swap happens, that means you're bringing a particular amount token of token zero to get a particular amount of token one, or you're bringing a particular amount of token one to get a particular amount of token zero. So that means if you're bringing token zero to get token one, that means the reserve of token zero will increase and the reserve of token one will decrease. So this block timestamp last will get updated again. So for every time there's a change in the reserve, this guy gets updated. So if you look at what I wrote here, say this keeps track of the last time the reserve was updated, right? And if you see, Uniswap did what we call variable packing here. So they ensure that these three variables are in one slot. So, okay, a slot is made up of it's the maximum amount of a slot is UN256. So that's the maximum amount a slot can take in UINT. So let me go to solidity shell. So like I said, a slot in a UINT slot, or a slot in solidity, or oh sorry, I say solidity. A slot in the EVM takes up to UINT 256, and if we say type UINT 256 dot max. So this is the maximum amount of units a slot will take. This slot will take, right? So now this is unit 112. So if you say unit 112, let's do 112 plus 112 plus 32. What does that give you? You in 256. So now that means this guy, this guy, and this guy, since they are grouped together like this, they will occupy one slot, and this is also a way of minimizing gas. Like, yeah, this is also a way of optimizing gas and all of that. So what they did here is called variable packing. So you can study more about variable packing as a smart contract developer and all of that. So let's move over to line 26. So line 26, the name of the variable is called price zero cumulative last. All right. So this variable is what the Uniswap price oracle uses to perform its magic or its logic. So let's look at it. So price zero cumulative last. This keeps track of the cumulative price of token zero each time there is a change in reserve zero. You get. So what happens is, let's say um let's say how will I explain this for you to understand? Okay, I will do the I might do this calculation, but it's not the most important thing in this contract. So if you might want to dig deeper into the board, I'll do the calculation if maybe I have a lot of time. But just know that this keeps track of the cumulative this keeps track of the cumulative price of token zero each time there's a change in reserve, and price cumulative one, this keeps track of the cumulative price of token one each time there's a change in reserve. So I think I performed a mass here for it. Let's see how Uniswap price oracle works. So you see cumulative price, each time it gets incremented each time there's a change in maybe there's a swap operation, or there's liquidity is provided or liquidity is removed. This stuff keeps adding to this stuff. It adds the new price, it does this mass and adds to this guy. So it's like a cumulative, it keeps incrementing, it doesn't go down. So but let's just leave it at that for now. There are a lot of things you need to understand before you understand these two guys. All right, so let's move over to care last. All right, so pay attention to this guy. Remember that I said, okay, in the part one of this video, if you watched it, I said that Uniswap make is an AMM. It's a decentralized exchange that makes use of the AMM mechanism. That's the automated market maker mechanism, and it's making use of what we call constant product. It makes use of constant product calculation, or constant product mechanism. Now, constant product K here is a constant, and the product now, what Uniswap does basically is the constant here is the product of reserve zero times reserve one. That is what is saving here. You get. So imagine, let's say the first time we are providing liquidity for this contract, let's say I am the liquidity provider and I want to provide liquidity for 1,000 uh, Shiba Inu token for 500 Dogecoin. Now, the care last, the care last at this time when I'm providing liquidity will be 1,000 times 500. So this will be the care last at that time. This is the product, the constant product of reserve zero and reserve one. Because once I provide liquidity, the reserve, this reserve zero will be 1,000 and this reserve one will be 500. So the K last will be this guy, which is 500,000. Yeah. So that will be the K last. So this K last is used in a lot of calculations in the contract. So is it a lot of calculation? It's used in, I think it's used in the mint fee function. So we'll see that when we proceed. But for now, just understand that this is what it holds. So this is, it's already here. Reserve zero times reserve one of as of immediately after the most recent liquidity. Yeah, the most recent liquidity when liquidity is added or removed. So it just stores the product of the reserve zero and the reserve one. All right. Okay, let's proceed. So on line 30, we have unlock equal to 1. So modifier lock require that unlock is equal to 1. Uniswap V2 lock, then set lock to 0. Then proceed to. So what this guy does, this is just used for re-entrancy. This is just used for re-entrancy. That's just the function of this guy. This whole guy now is used for re-entrancy, to guard against re-entrancy. So just know that. Just know that. So if you want to try and understand how this works, so I think I can do well to explain it. So at first, this guy is unlocked is equal to 1, which means unlocked is true, right? So now when you're performing a swap transaction, it first requires that lock is equal or unlock is equal to 1, which means it is unlocked. Now once this line is passed, it now set unlock to 0. That means it is not unlocked to 0, which means it is now locked. So once unlocked is 0, that means unlock is false, which means it is now locked. Then once this is done, this underscore here means it will now perform the operation which you ask it to do, right? Once it's done performing that operation and that operation has passed, it will now set unlock back to 1, which means it is now unlocked. You can now perform another operation. But for the time this law unlocked is 0, you cannot perform any other operation. You get? And this is for a particular user. It's not for, like, if it's unlocked for you, it's unlocked for you. Any other person can perform their transaction. So yeah, well, I really don't want to be explaining these guys all this small stuff like this modifier. You should be able to figure out what this thing does, because it will take a whole lot of time, and I really don't want this video to take a whole lot of time. All right, so let's proceed. Now on line 38, we have the get reserves. This is another way of Uniswap trying to do gas optimization. So what they are doing here is reading from states. Like if you're performing operations and you're reading from state, which means you're reading from storage directly from state, it costs more gas to perform operations while reading from state. So what Uniswap is doing here, you see this guy is called get reserves, right? So it's public view returns uint 112 reserve 0, uint 112 reserve 1, and uint 32 block timestamp last. So what they are doing now is they are now setting this reserve 0, that is a state variable. They are setting it to memory, setting this guy to memory, and setting this guy to memory. So anytime you want to make use of this reserve that is at the state, this guy that is at the state to this guy that is at state, which are all at storage level, it will just call this function and return them from memory. So it's returning them from memory storage, like from memory. So you won't have to be performing your operations. You won't have to be manipulating states when performing your operations. You'll be using them at memory. And after performing all your manipulation, your arithmetic, whatever, you can now update back the state. Not that when you're performing your whole operations, you'll be reading from state directly. No, it doesn't make sense. It costs more gas to manipulate state directly. So you manipulate it from memory, and at the end, you update the state. So that is what Uniswap is doing here. So this get reserve is like reading from state and setting to memory. So anytime you want to make use of all these reserve 0, reserve 1, block timestamp last, you just call this get reserve function, receiving the variables it's returning, and you make use of it, and that's it. All right. So we have the safe transfer. Now this is where that low level call was used. So now imagine you depositing, let's say you want to swap from token 1 to we want to swap from token 1 to token 0, and you bring in token 1, a particular amount of token 1, so that you can get a particular amount of token 0. This pair contract, we have to transfer token 1 to token 0 to you. If you're bringing token 1 to get token 0, so that means you first transfer token 1 into the pair contract, and the pair contract will perform its magic or its logic, and it will now transfer token 0 to you. Now this safe transfer is what does that transfer operation. So it first of all gets the address of the token that will be leaving, the address of the person that is receiving it, and the value that will be going to the person. So you now say, okay, bool success byte memory data. Now token, which is this token that's receiving here, dot call. This call is a low level call, and once you do dot call, you can now say abi.encode with selector. And once you say abi.encode with selector, it's expecting you to pass in a selector here. Normally you can pass in this guy inside that place, but now we have saved it as a constant. So what we are passing here now is this function selector that we saved here. So you pass in the selector here, then you pass in the value that this selector is expecting. Now, remember this selector is expecting an address. That is why we have the to, and this to will be an address, which we have here. Then value. This value now is uint256, which is this guy. You see here now they didn't put 256 because obviously uint by default is uint256. But when you're making use of it inside this function selector, you have to put it uint256 straight up, else you encounter issues. So you see we are receiving the value here, and that's what we are passing here. So this guy will perform this call, and this guy is requiring that this call is successful. So require success and data.length is equal to 0, or abi.encode data bool. Uh, so once it's requiring that this is successful, else it will tell you transfer failed. You get. So this is what this function is basically used for transfer operations inside the Uniswap V2Pair contract, and it's not making use of the basic transfer you and I know, the normal basic transfer. So it's using this guy. So Uniswap is doing whatever it takes to minimize gas, like, because if imagine if you're swapping on Uniswap and you're paying a whole lot of gas fee, that doesn't make sense. So they are ensuring that this gas fee is not coming from them, from their contract. If maybe there's increase in gas fee on Uniswap, it has to be because of Ethereum gas price spike or all of that, but not based on the inefficiency of their own logic. All right, so let's proceed. So on line 49, we have the event. The event means, so this is what this event does is it gets emitted each time a liquidity provider provides liquidity successfully. So this function is being emitted. It's called this event is being emitted, and this event is emitted in the mint function. And the mint function is the function that gets called when a liquidity provider provides liquidity. Then the burn event is emitted when a liquidity provider removes liquidity, because the burn function is the function that gets called when a liquidity provider wants to remove liquidity. So this swap guy gets emitted when a trader successfully swaps from one token to the other, and once that transaction is completed successfully, the swap event is emitted. Then the sync event. So now, for every time there's a change, in the reserve, this sync event will be emitted. For instance, after a swap operation, remember when you're performing a swap operation, you send in one token to get another token. So when you send in that token, you know that the reserve of that token needs to be updated. And when you send out another token, know that the reserve of that token needs to be updated too. So now, what does this is the update function. So the update function will update the reserve, and it will now emit this sync event to tell you that, okay, everything has been successfully synchronized, everything has been updated. All right. So let's move over to the constructor. Yeah, we all know what constructor is. The constructor gets called once a contract is being deployed. And like I said earlier, this V2Pair contract is deployed by the Uniswap V2 factory contract. And once you're deploying it, the message you're sender at that point in time is the V2 factory contract. That is the message sender. So it's setting this message sender to the factory state variable that was declared at the top at first. Yeah. So now let's look at the initialize function. So this initialize, like you said, yeah, this initialize function is called once by the factory at time of deployment. So what this does is, the moment the factory contract deploys this contract, immediately it sets the address of token 0 and the address of token 1. So what it does, first of all, it ensures that the address calling this function is the address of the factory, which was set here in the constructor. And if this line passes, then it now sets the address of the token that is passed here to this guy, and the address of the token that is passed here to this guy. And once that is done, voila, we now have our pair contract set with the two tokens that it will be swapping, that it will be exchanging, and all of that. So yeah, so that is what the initialize function does. And all right, so after the initialize function, what we have next is the update function. So this update function, I won't explain it now because you won't understand the update function if I explain it now. And this mint fee function, I won't explain it now as well. We are going to come back to it. So I want to explain this contract in the flow of how it works. You get? All right. So we are going to skip the update function and we are going to skip the mint fee function and go to the mint function. Now, from the mint function, we will now jump back into the update function and the mint function. Yeah, so that's the flow of how it will work. But let me see if I have something to read here. Let's see. So, okay, okay, we have this here. So this says, okay, the K last is a product constant of reserve 0 and reserve 1. So let me just put this in bracket and say reserve 0 times reserve 1. So that's what this K last is. Note, note, the pair contract only keep tracks the pair contract only keep track of reserves of the two tokens that makes up the pair. It doesn't store the actual token. Yeah, it doesn't store the token. It only keep track of the reserve of the token in the contract. So the pair contract uses the balance of address Ds and the transfer function to manage tokens. Yeah, we'll see how that works. It uses a low-level call to perform its transfer function. It gets the function selector of the transfer function. Then it implements the transfer function inside the safe transfer function using low-level call. The safe transfer function takes the address of the token to be transferred, address of the receiver, and amount of token to be transferred. So yeah, update function. Let's do this here. I'll just do this update function. So we'll talk about this from, so I already broke down the update function. So how Uniswap price oracle work, that's inside the update function. And also I have the mint function underscore mint fee function. So I'll also skip this mint fee function to keep this here. So we'll come back to this. I already performed the calculation for that here. Okay. All right. All right. All right. So let's go to minting and burning first. We'll come back to this guy. So minting and burning. Yep. So this low level function on this other side, so we have it on line 109 on the left hand side. This low level function should be called from a contract which performs important safety check. Now, pay attention. This mint function, now, like I said before, Uniswap is made up of two sections, the core and the periphery. The core is the part that does the heavy lifting. Like the core contains three smart contracts. That's the V2 ERC20, the V2 factory, and the V2 pair. You get now, but users don't interact with the core directly. You're not supposed to interact with the core directly. The reason is because um, you might the Uniswap core contract is written in such a way that you cannot cheat Uniswap. You cannot cheat the core. But if you're a user, you're calling the core directly without using the periphery, which is the router contract. You need to know what you're doing, else you will lose a lot of money. So what the periphery contract does is the periphery contract already does, that's the router contract, already does all the necessary safety checks for you not to lose money. So if you're calling this main function, the router contract will ensure certain things for you. So we are going to see that now. Before the router contract calls this main function, the router contract already ensures that you have already transferred the tokens you want to use in providing liquidity. For instance, let's say you want to provide liquidity for Shiba Inu. Shiba, why why did I choose to use Shiba Inu in this explanation? You want to provide liquidity for Shiba Inu and you want to provide liquidity for Dogecoin, right? And now you want to provide liquidity and you say you want to provide 1,000, or let me just use, yeah, let's use 1,000. You want to provide liquidity, you want to say 1,000 Shiba Inu for 500 Dogecoin. This is the liquidity you want to provide, because liquidity involves you bringing an amount of the two pair tokens and all of that. So before this mint function is called, the router contract will ensure that you have first transferred these two tokens to this pair contract before it will call this mint function. So before we proceed, I just want us to take a look at the router contract so that way you understand what's happening here. So let's go to the where is it? Where is it? Where is it? Let's go to the periphery contract. Yeah, router V2. So in this router V2, let's look for the add liquidity function. This is a private function. It's not this one we are looking for. Yeah, this is the guy we are looking for. So this add liquidity, now you see it takes the address of token A, the address of token B, which is this one will be our token 0 and our token 1. The amount desired, that's the amount of liquidity you want to provide. So for Shiba, here will be 1,000. For Shiba, here will be 1,000. For Doge, here will be 500. Amount A minimum, you put the amount A minimum. The amount B minimum, you put the amount B minimum. The address, this is now the address of the person calling this function. So this is going to be like the msg.sender. So this is the address of the person calling this function and the deadline and all of that. Now let's look at something. So uh, so pair. This gets the pair of the pair of the contract you want to provide this liquidity to. This is what we are looking at. Safe transfer from. Now look at what is happening here. It will first of all perform this transfer from. It will transfer this token from the person calling it to the pair and the amount. And it will now transfer the second token, this particular token, from the person calling it to the pair and the amount. You get? So this is what it's now doing. When it does this transfer, this is when it will now call the mint function. You see, liquidity is equal to UniswapV2Pair, the pair contract dot mint. Then it passes this address to, which is this address here. So I don't know if you get what is happening here. So before this, I'm going to close this router contract now. I just want to use it for explanation. So before this mint function is called, it will first of all send the token you want to use in providing liquidity here, right? So let's proceed. Let's proceed. Let's proceed. So this guy is making sense. So minting and burning. Okay, minting is when a liquidity provider adds funds that is provide liquidity to the pool, which leads to minting of new ownership token. That's the LP token. Burning is the opposite of minting. This is when a liquidity provider, this thing is liquidity, not liability, please. This is when a liquidity provider, uh, withdraws funds and the accumulated rewards and his pool ownership token. So LP tokens are burned, that's destroyed. So yeah, minting function. In the mint function, at first, Uniswap used a gas saving mechanism to save gas by transferring. Okay, so now let's proceed to the function proper. So remember where I was explaining this get reserve stuff. So you see, we are going to make use of the reserve 0 and we are going to make use of the reserve 0 and the reserve. Let me close this side pane. So we are going to make use of the reserve 0 and the reserve 1 here. And instead of reading this guide directly from state, we are reading it from memory, which is being returned from this get reserve function that I explained earlier. Now, remember that token has been transferred to this guy. So let's just do this guy. So I'm going to perform a little calculation here. So let's perform this calculation here. So let's do this. Let's do this. So this mean fee, right? So at first, remember that the reserve 0 and reserve 1 will be 0 because assuming we are providing liquidity for the first time, right? So let's just say let me do this here. I'm looking for a place to just perform my math. Okay. So let me perform my math here. All right. So let's assume okay, if liquidity is a brand new pool, this is the calculation that will be done, right? Let's just do this. Let me perform it here. Right. So now our reserve 0 at first, because we are providing liquidity for the first time. So here our reserve 0 will be 0. So let's say reserve 0 will be equals to 0 and reserve 1 will be equal to 0 as well, right? So because we have not provided liquidity for the first time. Now balance 0 will now be IERC20 dot balance. So now our balance 0 will be 1,000 because we have sent 1,000. Like I said, before this function is called, the token has already entered this contract. So balance 0, which is the amount of token 0 sent is 1,000, and balance 1 will be 500. So this amount of token 1 sent. So this is our Shiba, and this is our Doge coin, right? So now balance 0 is 1,000 balance. This guy is this thing. So now, in order to get the amount we actually sent, right? Because first of all, we get the balance. So we are getting the balance of this contract. In order to get the amount we actually sent, we now say amount 0 is equal to 1,000 minus 0, because at this point reserve 0 is 0. Sorry, this guy is supposed to be 0, not 1. And for us to get the amount 1 we sent, is going to be 500 minus 0, right? So now if someone else is providing liquidity, balance 0 will increase and balance 1 will increase. So to get the amount the person sends, you're going to say amount 0 minus 1,000 and amount 1 minus 500. You now get the actual amount the person sent. So, but in this case, since this is the first liquidity, is minus 0, and this will return. So our amount 0 will be equal to 1,000, and our amount 1 will be equal to 500. So I'm going to perform calculation for adding liquidity for both the first time and the second time, like the first time and the second, like when liquidity has already been provided for the first time. So now we have our amount here, so which is this guy. So fee on. So this fee on, now what this fee on does is it checks if Uniswap turned on fee. Now if Uniswap turned on fee, this remember that, okay, remember that, let me break this thing down. So remember that how Uniswap knows that you're going to participate in the sharing of the fee it charges traders from when swapping is by minting LP tokens to you. So if it mints LP token to you, that means you partake in that fee sharing. So what this mint fee does now is it will it will go if the fee is on. So let's check the mint fee. So now, like I said in the part where I say once the fee2 address is set, that means mint fee is on. That is why it's checking this guy. That's why it's checking fee on is equal to fee2 not equal to address 0. So if fee2 is not equal to address 0, fee on will be true. Address fee2, Uniswap V2 factory, you pass in the factory and you get the fee2. That this returns the fee2 address. So, and if it's not address 0, that means the fee is on. So once the fee is on, this thing you're seeing here, this math you're seeing here, this is the math that calculates 1/6 of the liquidity and it means it to the fee2, which means this fee2 is eligible to collect 1/6 of the fee, the 0.3% fee that Uniswap will be getting each time a user swap tokens on this pair. You get. So just understand that this mint fee means 1/6 of the liquidity that a user is providing to the fee2 address. 1/6. So if you're a mathematics person, like if you're a math genius, you know how to perform that operation now, that calculation. So just perform it and check it out. So that is what this guy is doing. So I will explain this guy. This video is already getting to an hour. So but I'm not going to stop this video because no matter how long it is, we don't have to break it so that users will follow to the end. So this mint fee guy now is what calculates the fee. If this fee is on, that means if if the fee2 address is set, means fee is on. And if that is true, it will mint 1/6 of the liquidity to this fee2 address, right? So let's go back. That's why I said I didn't want to touch this fee2 at first. So it is from the mint function that will now go to the fee2. So if that is done, so this is what it does. It passes the reserve here and it passes the reserve 0 here and the reserve 1 here. And remember, at this point, our reserve 0 is 0 and our reserve 1 is 0. So no fee will be minted to this guy. So check it out. Let's see. Let's go back to the main fee. Takes in this guy, takes in this guy. So careless, if this, so anything you're multiplying by 0 is 0. You see, anything you're multiplying by 0 is 0. So nothing will be minted at the first instance when you're providing liquidity. Even if the fee is on, nothing will be minted because 0, 0 is 0. Everything 0 is 0. You get. So just know that at the first instance, no liquidity will be minted to Uniswap. So no fee will be minted to Uniswap. Now, going to the total supply. This total supply is the total supply of liquidity that has been minted. Remember, we inherited Uniswap V2 ERC20 here. And once we inherit this, we have access to the total supply of this contract. And the total supply is increased each time. The total supply is increased each time this LP token is minted, and is reduced each time the LP token is burnt. So each time a liquidity provider provides liquidity, the total supply is increased. Each time the liquidity provider removes liquidity, the total supply is reduced. So now since this is the first time we are providing liquidity, that means no LP token has been minted. Automatically total supply is 0. We get that, right? So automatically total supply is equal to 0. Follow me while I take you through this ride of Uniswap V2 breakdown. I'm enjoying this actually. So let's go. On line 124, you see where we have if total supply is equal to 0, that means this is the first liquidity. This is the first liquidity that is coming to this V2 pair. And the calculation for first liquidity is different from the calculation from subsequent liquidity, right? Hope you get that. All right. So now, okay. So liquidity will now be math dot square root of this guy, this guy, this guy. So let's perform this calculation. So liquidity now, liquidity now will be equal to math dot root square root of what? Amount 0. And what is our amount 0? Our amount 0 is 1000. Amount 0 multiplied by amount 1, which is 500. Remember, so are you getting this gist now? Are you getting this gist? So amount 0 multiplied by this guy minus the minimum liquidity. Minus the minimum liquidity. So, and our minimum liquidity is, let's check our minimum liquidity. Our minimum liquidity is 10 raised to the power of 3, right? Let's look at it again. Minimum liquidity, yeah, 10 raised to the power of 3. And if we do 10 raised to the power of 3 here, this solidity shell, we get 1000. So minus 1000. Are we good? Are we good? Are we good? Are we good? So let's proceed back to our mint. Yeah. So this is where we are. So now it calculates the liquidity, right? So now what it does now, it now mints this liquidity to address 0. It mints this liquidity, this minimum liquidity to address 0. Now, once it means this minimum liquidity to address 0, remember that our total supply will increase to 1000 because it has minted 1000 to address 0. It's not minting it to anybody. The reason why it's doing this is so that now, subsequently, when users start providing liquidity or removing liquidity, you cannot go below this minimum liquidity. Liquidity can never get to 0. You get, because the minimum liquidity has been set and it's not minted to anyone who can come back and remove the liquidity. It's minted to address 0. So an address 0 cannot come back and remove liquidity. So that's why it's setting this. And that means our total supply, the minimum total supply we can get is minimum liquidity, even if everybody removes their liquidity from the contract. Is the logic clear now? So let's continue with our math. So let's now do 1000 times 500. This will give us this guy. So copy this guy and minus 1000. This will give us this guy. So now liquidity, I don't know where liability is coming from. Liquidity is equals to math dot square root of this guy, right? So let's do this stuff. So liquidity will now be equal to. So let me use my phone to calculate. Let me see if my calculator has square root. I don't know if this calculator has square root. Do you have square root, please? It doesn't have square root. So I'm going to use my calculator, to my phone calculator, to perform that math. So let's go to my calculator and go here, and I'll say square root of, what do we have? 499, and we have 30000. This will be this will be 706.3999. Sorry, 399323204 98. So Solidity doesn't support floating numbers because at this point they didn't make use of that. They didn't make use of that. What's it called? They didn't make use of that library here. So I will assume that the liquidity will be equal to 706. So this is what I will assume, because Uniswap didn't show us how they handle that floating stuff. So I will assume that the liquidity is 706. Now, once this liquidity is gotten, so it means minimum liquidity to this address. So here now, it will now require that liquidity is greater than 0. So it's requiring that what is calculated here is actually greater than 0. Else it will tell you insufficient liquidity minted. You get. And if this pass, it will now mint this 706 to the person that is providing liquidity. So that means the person that called this mint function will now get 706 of the ERC20 token. And now the total supply will now be, at this point, total supply will now be 706 plus 1000. This will be our total supply. So our total supply now will be 1706. So I don't know if you're getting the gist of what's happening here. This is exactly what, this is the mass that these guys are performing. Now, once this is done, the update function is called. The update function is called. Watch, pay attention, please. This update function now is now called. And let's look at the update function. The update function takes in the balance 0 and the balance 1. Remember, our balance 0 is 1000, our balance 1 is 500. Our reserve 0 is 0 and our reserve 1 is 0 as well. So it will now call this update function here, which takes in this balance 0 balance, this guy reserve this. Now it now requires that balance 0 is less than or equal to this guy, and balance 1 is less than. This is just a way that it uses this to ensure overflow. And then here it now says, okay, block timestamp is equal to uin32 block timestamp module this. But this is where it's performing this part now is using here now to perform its price update and everything. But this is what I want us to look at. You see here now it is updating the reserve with the balance. So now it will now say reserve 0 will now be equal to 1000 and reserve 1 will now be equal to 500. Then block timestamp last will now be the current block dot timestamp, like this stuff it performed here. It will now set it to this guy, and here it will emit the sync. Since it has updated this guy, it will emit this sync event, which was what I explained before, that the sync event is emitted once there's an update on the reserve and all of that. So it will emit this guy. We are going to come back to this price oracle calculation later. So, but for now, this is what I want you to understand. So this update is called, and it updates this guy. So you get what's happening. Forget about this price oracle here. This thing now you're seeing here. This is the price oracle of Uniswap. This small line of code. This is where Uniswap is performing their price oracle. That they're performing. Okay, if I give you 200 Shiba, I'll get so Dogecoin. If I give you 500 Dogecoin, I'll get so Shiba. This is where they're performing that magic or that logic you get. So let's go back to our mint function. And once this mint function is this update function is passed, fee on care last is updated. Remember, our care last is the constant product guy. So now, since our reserve has been updated, we'll now update care last. So care last now, previously care last is 0 because there was no the reserve 0 times 0 is 0. But now our care last will now be 1000 times 500, which will be 500,000. I don't know if you get that logic. Care last will be updated. So at this point, our care last. So let me just do this. So after uh, after this, right? After this, comma, reserves are updated and K last is updated too. So our new reserve 0 now will be reserve 0 now will be equal to 1000 and reserve 1 will be 500 and our K last at this point will be equal to 500,000. Are we good? So you see the logic. And after this happens, the mint event is emitted. You get the mint event is emitted, carrying the messages of sender, the amount, and this guy. I don't know if you get that, the logic. So this is you see the flow of how this logic is working. You get. So next thing we are going to be looking at is the bond function. Now, the bond function is the opposite of the mint function. So it's the opposite of the mint function. Now, like I said, the mint function happens when users are providing liquidity. So pay attention. You see, remember that the liquidity that is calculated here is now minted to the user, which in our case is a 706. You get, and this 706 is what shows that okay, you provided liquidity, and whenever you want to take out your liquidity, you're going to bring back this 706 Uniswap V2 token to take back your liquidity, and this is what serves that okay, you'll be getting a share from the 0.3% fee that Uniswap accumulates while swap transactions occur. All right, let's proceed again. Now, remove liquidity. This also should be called or should be performed by by a contract which performs important safety check. So removing liquidity also is being done by the peripheral contract, which is the router contract. All right. So the bond function is called when user is removing liquidity, and also see all this lock. See this lock here that I told you is used to prevent reentrancy attack. So once you call this function, lock is activated. Until that function is passed, the lock will now be open again for you. All right. So same way again, this reserve is gotten from the get reserves. So the address token 0 is gotten, token 1 is gotten from state. So we won't be manipulating state again. So the first thing this guy does here, it gets the balance of address, the balance of token 0 for address this, right? And it gets the balance of token 1 for of this address. Then liquidity is equals to balance of address this. So it tries to get the balance of address this. That's the liquidity this contract has for the ERC20 token. That's the Uniswap ERC20 token. So it tries to get the balance of this address. So if mint fee is on, again, it means, so at this point reserve 0 is 1000 and reserve 1 is 500. So it will now mint it will mint 1/6 of this guy to this uh, to this Uniswap contract, right? Then it gets a total supply. So let's just perform this math. Let's perform this math. So let's go to the bond function. Let's go to the bond function. So okay, let's read this so we get something. The bond function is the exact opposite of the mean function. The same gas saving mechanism is used just like in the mean function. Balance 0 and balance 1 are total balances of the pair tokens in this pool. Balance 0 is okay, IRS balance of address this and this. Liquidity balance, okay. Liquidity is the amount of pool ownership token that the liquidity provider who wishes to cash out has. You get. So, but first of all, it gets the liquidity or the balance of this address. Now, question is why why okay. Yeah. Now pay attention to this. This part might confuse you. I intentionally asked this question here. So pay attention. Normally, if you want to get liquidity, the liquidity you're getting should be the liquidity of the person that is calling this contract and not the liquidity of this contract. But why is it checking liquidity of address this? That's the balance of address this for the ERC20 token. That was why I asked this question here. So, but do we supposed to be why do we access the liquidity of the balance of address this? You understand? So now answer is because the liquidity was transferred to the pair contract by the periphery router contract before calling the bond function. So before this means that the balance of address this for this token will always remain 0. So anytime liquidity is to be removed, the user that is removing liquidity will first of all transfer their liquidity token, that's their LP token, to this address before calling this bond function. The same way, if liquidity is being provided, they'll first of all transfer the tokens they want to use in providing liquidity to this address before they call the main function. So when they transfer the liquidity to this address, given that the balance of address this for the LP token is always 0, so any amount it's seen now is the amount of liquidity that the person that is calling this function is sent. And at that point in time, it will now check if this guy is on total supply. It does this. So amount, okay, let's perform this math. Sorry, let's just do this math here. Where will I do this math? Okay, let me run this math here. All right. So given that at this point our reserve 0 is equal to 1000 and reserve reserve 1 is equal to 500, right? Now we have gotten our token address. The reason why we are getting this token address is if we want to perform a transfer. So now balance of address this for this stuff will now be balance 0 balance 0 since no swap has been done. Balance 0 of token, this guy will be 1000 and balance 1. So remember, these things are just scenarios we are painting, not as if this is the actual story. We are just painting scenarios of how this would be. But before you remove liquidity, trade must have already, a lot of swap must have already occurred. So now no swap has occurred. We are assuming no swap has occurred at this point in time, and you want to remove your liquidity back, right? So now remember that the person that provided liquidity, the liquidity that was given to the person here is 706. Where is it? is 706, right? So this person now is going to transfer that 706. Let's say the person wants to remove all their liquidity. So what will happen here now? The liquidity will be equal to 706, right? So fee is on, it's going to mint 1 over 6 to the FITO address. Now, total supply at this point now will be, what will be our total supply? Hope you remember. So our total supply at this point will be this guy. So there's supposed to be an equal to here and also here. Yeah, our total supply is 1006, 1706. Where is this guy? So total supply will now be equal to this because it minted those guy and that guy. All right, so we have gotten our total supply. So amount zero, that's the amount zero, amount zero will now be equal to, see the math here. Let's perform this math. So yeah, so I want us to perform all this math. Amount zero is equal to liquidity multiply. So our liquidity now is this guy, right, times balance zero, which is this guy, Now both of these will be divided by total supply, which is this guy. Whoa, are we good? So now this is what's going to be our liquidity. So let's perform this math here. 706 times 1000 is equals to this. All right, so let's copy this. I like breaking this in steps so that this will now be equal to this guy divided by 1706. So I hope this division will not cause overflow or underflow. And it might lead to decimal, and if it leads to decimal, Solidity share will throw an error. So let's check this out. I know Solidity share will throw an error. So let's just use calculator to perform this guy. So here we now have our calculator. Come up for this. Paste this guy here. Divide by 1706. Divide by 1706. So this gives us 413.83. So amount zero is equal to 413 point, can I copy? 8335. So let's just do 8335. But Solidity doesn't support decimal, so amount zero will be equal to 413, right? 413. Okay. So let's look at amount one. So amount one will be, let me copy this guy. Amount one will be this guy. Amount one will now be this guy. So let's say amount one will now be equal to, liquidity is 706 multiplied by balance one, and balance one is 500. Yes, so multiply by balance one, put this guy here, divide by total supply. Our total supply is this guy. So once you put this guy here, so let's do 706 times 500 gives you this, and yep. So amount 1 will be equal to this guy divided by 1706. So copy this guy. This thing will still throw error for us. Divide by 1706. Give us error. So let's go back to our calculator. So clear this guy, paste this guy, divide by 1706. Hit it. This will give us 206. This will give us 206. 206.9167. 206.916, please. So amount 1 will be equals to 206.91676. All right, so this will be amount 1 will now be equal to 206. So now notice when we're providing liquidity, we provided the user provided 1,500. But when they want to remove liquidity, they can't get that guy again, because now they are the first person that provided liquidity, and minimum liquidity has already been done, like the calculation has been done. So you can't remove everything you provide. You can't. So the best way to benefit from this is to allow trades to happen, for people to keep providing liquidity and all of that. So when trades keeps happening, you will get your 0.3% share of the whole trade that is occurring. And whenever you want to remove liquidity, you make money, you get interest. But if you remove your liquidity immediately when you provided it, and being the first person that is providing liquidity, you're going to obviously get less, because the minimum liquidity has been done, like minimum liquidity has been calculated and all of that. So you see, in that calculation, you can't get exactly what you imputed. So now, see what's now happening now is that say require that amount 0 is greater than 0 and amount 1 is greater than 0. Hence, tell you insufficient liquidity bond. You understand? So it will now burn this liquidity that you sent to this address. It will burn it, it will destroy it. And once it burns it, this address, the balance of address this now becomes 0 again. Now it will now save transfer token 0 to your address and this amount 0, which is this guy, and it will save transfer token 1 to your address, which is this amount 1. You get. And once this is done, remember, it has transferred this guy to you. It has transferred this guy to you. So the address, the new balance will change. So first of all, note the new balance. So balance 0 will now be equal to the previous balance 0, which is 1,000. Sorry, which is 1,000 minus this guy, this amount, right? So, and let me just take this to Solidity share and get the value. So this will return 5. So balance 0 will now be equal to this guy, right? This is the updated balance 0. And balance 1 now will be equal to 500 minus 206. So this will now be this guy. This will now be balance, balance 1. This will now be equal to 294. So this will now be our new balance 0 and balance 1. Then now we'll call update function again. And remember what update functions does. Update functions will now take the new balance 0 and balance 1 and update the reserve. So our reserve now will now be equal to our due reserve. So once that update is called, our reserve 0 will be equal to 587 and our reserve 1 will be equal to 294. And once this is done, remember the k last is updated again. So reserve will now be 5 this times this. So our k last at this point will be equal to this guy times 294, which will now be this. This will now be our k last at this point in time, right? And the bond function, the bond event is emitted. So I don't know if you're following, if you're getting the logic of what's happening here. So this is exactly what's happening here. So this is interesting. So yeah, I don't want to make this video longer by trying to provide liquidity for the second time. Like, okay, what if liquidity has been provided and you want to provide liquidity again? So if liquidity has been provided and you want to provide liquidity again, this is the mass that will be done. This mass here is what will be calculated, this particular mass here, because total supply at this point will not be equal to 0. So this is the mass that will be used to calculate the liquidity that will be minted to the person providing liquidity at this point in time. You get that? So you can test, you can play around this part and see what happens and all of that. So next we'll be looking at the swap operation, and let's see what happens here. Let's see what happens here. This is really getting interesting. Although the video is longer, but I don't want to make it short. I don't want to cut this video again. So we go through the end of this and all of that. Yeah. Okay. So all right. So now we are going into the swap function. So this is really Uniswap protocol is really an interesting one. All right, so let's look at the swap. Awesome. All right, so the swap. Let's just look at my notes over here. So the swap function is used by traders to swap tokens. So the swap function ensures that the amount of token you are swapping, the amount of token you are swapping is greater than 0. Okay, yeah, this is on line 168. So it ensures that the amount of token you are swapping is greater than 0. It can it can be any of the tokens in the pair. So only one of the tokens can have a value. It doesn't matter. It doesn't matter. So it also ensures that the amount of token you are swapping from and the amount of token you are swapping to is less than the available reserve. Hence, it will throw insufficient liquidity. So what this means that, for instance, now, if maybe what you have in the reserve is if maybe what you have in the reserve is 500, for instance, token 1, you have 500 token 1 in reserve. You cannot be swapping out 1000 token 1. Sorry, let's say you have 500 token 0 in the reserve. You cannot be swapping out 1000 token 0 because it exceeds the reserve of token 0 in the contract. And similar here, if you have 1000 uh, token 1, the reserve of token 1 is 1000, you cannot be swapping out 2000 token 1. That is what this guy is assuring, that you cannot be swapping more than what the reserve has. All right. So all right, it ensures that okay, yeah. So if the checks are passed, okay, It checks if the checks are passed. It checks which of the amount out and amount that is greater than zero. Okay, whatever. So what is happening here now is it it sets a local variable, that's a memory balance zero, and this guy balance one. So this for token zero and token one. So here now it now says address token zero is equal to token zero. So this is like same gas optimization. Is bringing the state variable and setting it to memory, and address token one is token one from state. Okay. So here it says require that the tow address, require that I like giving space so that we'll see what's happening here. Require that the tow address is not token zero and tow address is not token one. So you cannot be sending you cannot be swapping token to the token address itself. So it's checking this. So invalid to address. So it's checking that the address that it is swapping to is not any of this address. So this is just sanity check. Yeah. So if amount out is greater than zero, safe transfer token zero to amount out. And if amount one is greater than zero, uh, safe transfer amount token one to to the address and amount out. Now, so you will have a question. If normally you're supposed to ask a question that why is it just transferring out without first of all checking that the amount that the person is meant to bring in has already been brought in, right? So yeah, that was done. I'll show you when that was done. So yeah. So let's do that. So let's just go to this note. So if checks are passed, it checks which of the amounts out, that's amount out or amount zero out or amount out that is greater than zero. Then it transfers the amount out to the trader optimistically. So note, without making sure that the trader has already transferred corresponding token into our balance, we can optimistically transfer tokens out because the swap function have assertions later in the function to check if we receive corresponding tokens. The peripheral contract should send in the tokens to the pair contract before calling it for the swap. If the pair contract have not received any tokens, assertion will fail and Solidity will revert the entire function. So just like in the liquidity pro, the mint function, where before you call the mint function, the peripheral contract has already ensured that you transferred the tokens you're meant to use for providing liquidity into the pair contract. So here, before you swap, the peripheral contract that calls the swap has already, first of all, make sure that you have sent in the token you want to bring in order to get the token you want to take out. So it will first of all ensure that. So, but here we didn't perform the check here. So we said if amount out is of token zero is greater than zero, transfer this guy to the person. And if amount one or out of token one is greater than zero, transfer this guy to the person. Then, if data.length is greater than zero, this is where it will now initiate this calling. So let's look at this thing. So the code, if data.length is greater than zero, this guy. So we'll inform the receiver about the swap. This is like when you're performing a swap, you see where the front end will pop up something like it will pop up for you to confirm or do any of those stuff. So this calling will inform the person that is calling this swap about this swap and all of that. So once this guy is passed, then this is where it now does the check. It now say balance of I-20 of address this and balance of I-20 of token. So token 0 and token 1. It checks the balance of token 0 and the balance of token 1 of this address. Now, it now checks the amount in of token 0 and the amount in of token 1. And so let me just go here. I did this math already. So let's assume that our reserve is 0. is 1,000. Our reserve zero is 1,000, right? So let's assume we didn't remove liquidity after providing it, and our reserve zero is 1,000, and our reserve one is 500. Now a user is swapping 100 token zero. This means the user is going to get 50 token one, right? Using this ratio now, we have not gone to, I'm just assuming this now. So now incoming token one is 100. Incoming token zero is 100 because the user is swapping from token zero to token one. So incoming token zero is 100. Incoming token one is zero because the user is not swapping from token one. So incoming token one is zero. Outgoing token zero is zero because the incoming is token zero and the outgoing of token zero is zero. But the outgoing of token one is 50 because we are swapping 100 token zero to get 50 token one. At this point, since the user has sent in this guy first, and as this guy has already transferred this guy out, so at this point balance zero is 1,100 because the reserve is 1,000 plus 100 that the person sent is 1,100. But now here now balance one will now be 500 minus 50, which will be 450 because it's sending out token one. That is why if you see here now, if amount out of token amount zero out is greater than zero, it transfers token zero. But now amount out of token zero is zero, so it's not transferring this guy. If amount out of token one is greater than zero, it transfers token one to the person, and amount out, and here it's transferring 50. So if it transfers this 50, that means it's 500 minus 50 is 450. You get that? It does this guy. So this guy is still within the function. So here now, this is where it's performing its check. So now, using this formula, amount in is equals to balance zero greater than reserve. So if I'm talking too much, so let's see. Let me just expand this guy so we get to understand what's happening here. So is amount in is balance zero greater than reserve zero minus amount out. If that is the case, so the balance zero is what amount in is balance zero minus reserve minus amount this guy. This whole ternary operation gets confusing sometimes. So let me just explain this here. So amount in balance zero at this point is 1,001. Now, is balance zero greater than 1,000 minus zero? Yes. So what is happening here? Balance zero minus, in bracket, 1,000 minus zero. So what we are having here is 100, right? Now amount in 450, is 450 greater than 500 minus 50? No, because 500 minus 50 is 450, and this thing here is 450 minus 500 minus 50 is 450. This will return zero, this will return zero. So amount in for token one is zero, but amount in for token zero is 100. That is what is happening here. You can perform this math on your own to see how it works. So I don't know if I'm able to explain it well. So I'll send this doc so you see it. So this is where this guy happens now, and that's what's happening here. Yeah, that's what's happening here. So it gets the balance, it gets the amount that is coming in for token zero, and it tries to get the amount that is coming in for token one. But since token one, no amount came in, this will return zero, while this will return 100 in our case here, in our use scenario. So require that amount zero in is greater than zero, or amount one in is greater than zero. Else to tell you insufficient input amount. So there's an or statement here. It has to be either this or this. So now balance adjusted. So this was happening here now. So if amount in of either token of the pair contract is less than 0, it will revert insufficient input amount. So now, once it checks this, if any of this is 0, if it's 0, this is where this whole function will revert if you didn't send in any amount at first. If you didn't send in any amount, this is where the whole function will revert. But now the peripheral contract ensures that you send in the amount in to get your amount out. So you cannot cheat this smart contract. So it says if the amount in of either token of the pair contract is less than 0, it will revert insufficient input and the entire function will revert and nothing will have taken place. You get that? Now if the checks passes, then it proceeds to the 0.3 fee paid by traders. So 0.3% fee paid by traders is calculated. It does this calculation to check and ensure that the fee was paid. Note that the fee is also transferred to the pair contract, and this is made possible by the router contract. So the same way you're transferring your amount in to this contract, the peripheral contract also ensuring that you're transferring the 0.3% fee as well into this contract. So now this is where we perform the whole calculation of the adjusted, so the whole calculation of the fee. Now let's say you were given a task to modify this contract so that it will be charging 0.5% fee. All you just need to do is change this 3 to 5. Change this guy to 5. You get? Or if you are asked to collect 0.1% fee, change this guy to 1, change this guy to 1. You get? But now it's collecting 0.3% fee, and that is why we have 3 here. And the rest of this guy, he performed the rest of this calculation here. Then it calls this update function again. Because once you're swapping, the new balance will change because you sent in out some token and you collected in some token. Then you have to now update your reserve again. Once you update your reserve, the swap event is emitted. Now, the peripheral contract, let me show you where the peripheral contract ensures that you're sending the fee as well. So I'll have to show you that so you see this guy. This video is getting to 2 hours. Well, I don't know this. I can't help it. It's just the contract. The contract is large. You have to understand it. All right. So in the peripheral contract, yeah, let's go to the peripheral contract. This is the router. Let's look for where we are swapping. Let's look for where we are swapping. Let's look for where we are swapping. Okay, yeah, underscore swap. Yeah, swap exact tokens for tokens. All right. So now this swap exact token for tokens. See, it says amount is equals to, so this is the amount. It wants to calculate the amount out and the amount in and all of that. So amount equals to UniswapV2 library get amount out. So factory amount in part and all of that. So now this get amount out, this is where it's calculating the fee. So let's locate this library. I want you guys to pay attention. Let's locate this library. UniswapV2 library. So let's look for get amount out. Oh, get amount out. Get amount out. Yeah. So now get amount out. See what is happening here. Amount in with fee. Amount in multiplied by 997, right? So now, if remember that this guy is if this guy is supposed to be 1 1 2 3, but now it is 997, which means 0.3% is calculated here. If it was supposed to be 0.2%, this would be 998, and in your pair contract, this would be 2. So I want you to pay attention to this. You understand? And if you want to, if you want it to also calculate 0.1% fee, this should be 999, and here this should be 1. Are you getting the? And this should be 1. This should be 1 as well. So this is where it's calculating the fee, whether 0.3% fee is being calculated. So I will really beg that I don't want to stretch this video further. Like I don't want to stretch this video further. So I will have to not continue go further into explaining this whole percentage calculation. I will just stop it here for for the percentage calculation. Then let me revert this back to 997. So you can dive. I've already done justice to explaining this smart contract, to how it works and how the what each of these function does, right? So you can dig deeper into exploring how this percentage and all these things are being calculated, because this video might get to 3 hours if you want to break down everything bit by bit. So there are two more functions I need to touch in the V2 pair contract. So before I end this video, all right. So this is the scheme and the sync function. So let's look at the scheme and the sync function. I did some crazy mathematics here, but because of time, I won't take this video any longer, please. So but I'll be sending this documentation here, so you can follow it and try to play with scenarios and see what's happening. So scheme and sync function are needed when balanced on the ERC20 contract of the exchange token. When need on scheme and sync function are needed when balances on the ERC20 contract of the exchange token fall out of sync with the reserve variables. So in the pair contract, this can happen, for example, when someone just when someone just transfer Dogecoin to the pair contract account for no reason. There are two solutions to this to keep the reserve variable. So what's happening? The reserve needs to always be in sync with whatever is happening with the balance and all of that. So imagine someone just decides to send Doge token to the pair contract. The person is not performing swap, the person just sends it. You know that at this point, the balance will be more than the reserve. The balance will exceed the reserve, and the update function will not be called to update the balance with the reserve at that point in time. So this scheme and sync function are used to enforce that the balance is always equivalent to the reserve. This function can be called by anyone, you get. So this function, once it's called, so the scheme function, it allows someone withdraw the extra funds from the pair contract. Anyone can call this function. So the scheme function forces the balance to match the reserve. So if you look at it, it just safe transfer the extra token that is in this balance to the person that's calling it. So it subtracts the reserve from the balance of and sends the token out. So it forces the balance to be equal to the reserve. Same thing with the sync. So the sync function forces the reserve to match the balance. So it calls the update and all of that. So that is just what these two function does. So I believe I've been able to do justice to this smart contract. I think this is the best Uniswap smart contract breakdown you get on YouTube. Trust me. I've been able to do justice to this to the best I can. I don't want. I could have explained this mint fee function. Remember, I said I would have done that, but there's no this is getting to 2 hours, and when the video gets too long, it becomes boring and yeah, all of that. So yeah, but I did the explanation in there. I documented something in this docs, so you can go through these docs and you should be able to understand what's happening there. So, but just know that here is where Uniswap did their price oracle stuff to get the ratio of what a particular token will give the other token, of the amount of a particular token that will give the other token, and all of that. And here, this particular place is where Uniswap is calculating the 1/6 of the entire fee that will go to Uniswap if fee is on. That's if the fee2 address is set. So Uniswap will be taking 1/6 of the entire 0.3% fee that liquidity providers are meant to share. That's what this part of this part does. So it calculates that 1/6 and mints it to the fee2 address. This is where it mints it to the fee2 address. So you can take more time to try to understand what's happening here and all of that. So if you want to manipulate the amount or the ratio of what Uniswap will be taking each time someone provides liquidity or someone removes liquidity, this is what you modify. You can modify this to 3, you can modify this to 4. But before modifying it, I need you to understand what is happening here, what is really happening here. Once you're able to understand what is happening here, you know why this 5 was used, and you can always modify it to anything you want. So I've been able to show you 3 areas where you can modify the Uniswap contract to suit whatever you want. This is one. This place is one. This place is 2. This is where they are calculating the fee, and the library. So this is another place. All this place is where they are calculating the fee. So if you're changing anything in the fee part, let's say you're changing it to 0.2%, this will have to be 8, and here also will be 8. Take note of this, because this is what you need mostly when working with Uniswap. A company might just tell you, okay, we need a decentralized exchange and we need to be taking 0.5% fee and all of that. So I'm showing you the target points where you need to modify to achieve those things and all of that. So, but you can do more research to understand what is happening here, how this is being calculated, and all of that. So I'll be providing resources for how I was able to study about Uniswap, the resources I use in studying this and all of that in the description. So if you have any question, maybe you got confused at some point, you didn't get a particular thing, you can do well to ask questions in the comment section, and I will be so willing and available to provide answers to your questions. And we have come to the end of this video. It was a very long ride. If you got to this point, you're awesome, you're lovely, and yeah, you're breaking into DeFi. So subscribe, turn on the notification bell. You get more of quality content like this subsequently. And I remain Kaswini Ojuku. Peace out. Yeah, you can also follow me on Twitter, the Coding Cast. Yeah, peace out. Have fun. Bye.